Usually when we talk about high-end engineering, there's this underlying expectation of just absolute perfection. I mean, you think of a Swiss watch,
Oh,
right?
yeah, the classic example.
Yeah, exactly. Every tiny microscopic gear, every jeweled bearing, every coiled spring, it's all just meticulously planned to interlock flawlessly.
It is. It operates entirely in this binary state.
Right.
Like the mechanism is either functioning in a state of absolute factory perfection, or it has catastrophically failed.
Just a paperweight at that point.
Exactly. There's no, middle ground where a Swiss watch suddenly figures out how to keep time with three missing gears.
Yeah, and we build our machines that way because, well, it's comforting. We like predictable
They
systems.
do.
But then if you look away from the machine shop and you look at nature, you look at an animal surviving in the wild, suddenly that binary of like perfect or dead just goes completely out the window.
Because the natural world doesn't care about perfection.
Right. We're looking at a survival landscape that is fundamentally messy. A coyote doesn't just, power down into a blue screen of death if it steps on a sharp rock and injures its paw.
No, it adapts. It limps.
It shifts its center of gravity instantly.
Right.
And today, we are looking at a blueprint to give machines that exact same biological instinct.
Which is an incredible leap forward.
It really is a system where a robot with a snapped leg on a remote asteroid doesn't just sit there waiting for a repair crew that, let's face it, is never coming.
Right.
But instead, it literally hallucinates a new way to walk in a matter of seconds.
It's fascinating.
So for you, the listener, whether you're into robotics, biology, or just, fascinated by how complex systems survive chaos, this deep dive is going to completely change how you view resilience.
I completely agree.
We're unpacking this incredibly dense, paradigm-shifting white paper today. It's titled Self-Repairing Legged Robots.
And the core mission of this deep dive is exploring an architecture designed for autonomous robots operating where no human can reach them.
Right, like undersea trenches, collapsed mines, off-world colonies, places where you can't just send a mechanic.
Exactly. The author of this architecture isn't just trying to build, a better diagnostic tool.
Right.
The overarching philosophy here is that in these extreme environments, restoring the robot to its original factory condition is just impossible.
The limb is gone.
The limb is gone, the servo is fried, whatever. The goal shifts entirely from repair to survival.
Survival.
Yeah, it's about finding the nearest workable substitute behavior and finding it fast enough to complete the mission before the whole system just collapses.
Okay, so let's unpack this shift. Because going from the rigid, centralized brain of a traditional robot to something that limps and adapts like a wounded coyote, that's a massive leap.
It's a total reimagining of how we control machines.
And to understand how these robots are built, we really have to start with why they're designed this way. And the paper traces this whole philosophy back to a very specific and honestly kind of surprising biological observation.
Yeah, the cane toad.
Right, a cane toad hunting a mealworm.
Which sounds random, but the cane toad's frog is this brilliant example of what roboticists call a complete sensorimotor act.
Break that down for me. What does that mean in action?
Well, when you observe a cane toad hunting, it acquires the target visually, it estimates the physical range, it manages the internal timing, and then it executes this incredibly fast ballistic commit of its tongue to catch the worm.
And it rarely misses, right?
Right. It does all of this with really high reliability. But what's crucial here, what the author is really pointing out, is that it accomplishes this on incredibly minimal neurological hardware.
So it's not sitting there like a supercomputer running some massive calculus equation to perfectly plot the trajectory of its tongue.
Not at all. I mean, a traditional robot would have this massive central processor taking in camera data, building a 3D map, calculating wind resistance, determining the exact voltage to send to the tongue actuator.
Sounds exhausting.
It is. It's computationally heavy, and it runs this continuous feedback loop. But the toad doesn't do that.
The intelligence isn't sitting in a central brain.
Exactly. It's not doing deep deliberation. The intelligence is physically baked into the mechanism itself. The author brings up a concept here championed by a researcher named R. Pfeiffer. It's called morphological computation.
Morphological computation, okay, meaning the actual physical shape of the body is doing the math.
That's a great way to put it. Think about human running, for instance.
Okay.
If you try to program a robot to run by calculating exactly where every single joint should be at every millisecond, it's a computational nightmare.
Right, there's just too many moving parts.
But human legs, they have tendons that act like literal springs. So when your foot hits the ground, the tendon stretches, it stores kinetic energy, and then it releases it to push you back up.
Oh, wow.
Yeah, your brain isn't calculating that energy return. The physical structure of the tendon is doing the computation for you naturally and instantly. The body's offloading the control work onto its own physics.
That makes so much sense. I mean, if the body's doing the heavy lifting, the brain doesn't have to micromanage every single millimeter of movement. But, okay, what does that mean for designing a robot for an asteroid? A robot isn't a toad.
True, but the principle dictates that resilience has to live at the edges. It has to live in the body and in the local controllers at each individual joint. It can't just sit in some massive, flawless central plan.
Because if you rely on a mathematically optimized central plan, what happens the moment a physical leg snaps against a rock?
The plan shatters.
Yeah, the reality no longer matches the math equation.
Right. The central computer will just keep blindly sending the walk forward command, assuming it still has 4 perfect legs.
And the physical outcome is entirely wrong, and the robot just flails itself into the dirt?
Exactly. Because in remote deployments, failure modes are usually deeply mundane. It's not usually a massive software glitch. It's a broken servo or a joint packed with abrasive lunar dust or an off-center load.
So a centralized system is just incredibly brittle to physical realities.
Yes, highly brittle.
It's like the difference between a highly managed corporation where every single minor decision has to be routed up to the CEO.
Oh, that's a good analogy.
Right. Versus empowering a local branch to just handle a crisis on the fly without calling headquarters. If the local branch waits for the CEO to draft a perfectly optimized global recovery strategy, the business goes under. They don't need a perfect plan. They just need to keep the doors open today.
That's exactly it. And that urgency is actually rooted in the author's background in hard real-time control systems.
Oh, interesting.
Yeah. The paper notes this design sensibility was carried over from working on scientific instrumentation, specifically an optical trapping system.
An optical... Wait, is that like using lasers to hold things?
Essentially, yes. They are sometimes called optical tweezers. You use a highly focused laser beam to physically hold and move microscopic objects, like individual cells or even atoms.
Okay, wait. Holding an atom with a laser beam sounds like it requires mind-bending precision.
It does. The author mentioned steering this laser through an acousto-optic modulator, and it was all running on a real-time Linux kernel.
Right. But why does it matter that it's running on real-time Linux instead of just, a regular computer?
Because of deterministic deadlines.
Deterministic deadlines.
Yeah. In a standard computer, if you open a web browser and the CPU is busy, it might take an extra half-second to load. No big deal.
Sure, you just wait a second.
But in hard real-time control, if you are steering a laser to hold a vibrating atom, the control loop must close within a mathematically guaranteed deterministic window, say exactly 1 microsecond.
Wow.
If the computer takes a microsecond and a half to think about the correction, the atom is already gone. The measurement is completely lost.
Yeah.
There's absolutely no, give me a second to process this in real-time systems.
Ah, I see. So it's unforgiving. And that exact same brutal discipline is being applied to the injured robot.
Yes. The author treats a broken robot leg exactly like a drifting atom. A recovery that cannot be computed and physically committed inside the available time window is not a recovery. It is a fatal failure.
Because if a robot is on a steep lunar incline and it breaks a limb, and its processor takes an hour to calculate a new gait.
The battery might die, or gravity might just pull it off a cliff in the meantime.
Right, it doesn't have an hour, so the system is incredibly constrained by time, which leads to the biggest puzzle here, I think.
Okay, what's that?
If the central brain isn't micromanaging everything, and the robot only has a few seconds to react, how does it actually know it's broken? When a joint snaps without a central brain doing a full system diagnostic, how does it figure out a new way to move without just thrashing around and destroying whatever hardware it has left?
It is the foundation of this entire architecture.
Mm-hmm.
It uses a self-model, what the paper calls the avatar.
The avatar. I love that name.
It's very fitting. When this robot detects that something is wrong, it doesn't just start twitching its broken leg blindly. It loads up a highly detailed mechanical simulation of its own physical body.
So it maintains an internal virtual representation of itself.
Exactly. And if a structural fault is detected, say a servo stops responding or a sensor indicates a mechanical linkage has snapped, that exact damage is inflicted on the virtual avatar.
Right. Or if the robot is suddenly carrying an unbalanced payload, the avatar is loaded with a virtual offset mass to match.
Precisely. It evaluates thousands of candidate recoveries against the predicted physics in the simulation, long before it risks sending a single command to the physical motors.
Here's where it gets really interesting for me. It's essentially retreating into a mental holodeck.
A mental holodeck, yes.
It's imagining its own physical trauma and then daydreaming different ways to walk with the limp inside a safe, simulated sandbox. It's like mental holodeck physical therapy.
That is exactly what it is. And the paper actually cites a massive milestone in robotics for this concept. It's the 2006 Resilient Machines, work by Bongard, Zykov, and Lipson. It was published in the journal Science.
Let's dig into that precedent because that 2006 paper sounds like the grandfather of this whole idea. What exactly did Bongard and his team build?
They built a physical, four-limbed robot, somewhat shaped like a starfish. It had about 15 motors. But what was groundbreaking was that the robot didn't start with a pre-programmed idea of what it looked like.
Wait, really?
Really. It started by performing semi-random twitches. It would move a motor, read its tilt sensors, and then use that data to synthesize multiple competing virtual models of what its own body might look like.
So it was born physically blind to its own shape and had to guess its own structure just by feeling how it moved.
Yes. It would generate, say, 16 different simulated bodies that could all theoretically account for the sensor data it just received.
That is wild.
Then it would find an action that would produce a different result in Model A versus Model B. It would perform that specific action in reality, look at the real sensor data, and discard the models that guessed wrong.
It acts like a scientist performing experiments on its own body.
Exactly. It continuously refined its avatar until it had an accurate internal picture of itself, and then it used that avatar to figure out how to walk forward.
But the real test, if I remember correctly, came when the researchers physically sawed off part of one of its legs, right?
Yes, they literally sawed it off. And the robot's sensors detected that its real-world movement no longer matched its internal avatar's predictions.
Oh, wow.
So it stopped trying to walk, went back into the twitching phase, generated new data, updated its avatar to reflect the missing limb, and then evolved a completely new limping gait inside the simulation to keep moving forward.
Which proves the concept perfectly. Simulating the damage protects the hardware from further destruction while you figure out a fix.
Right.
But there is a massive catch here, isn't there? I mean, a simulation is just math. It's a video game. And a video game isn't the real world.
You're referring to the reality gap.
Yes, the reality gap. The difference between the frictionless, perfect math of the holodeck and the messy, gritty reality of standing on an asteroid.
The reality gap is one of the hardest constraints in autonomous robotics. The avatar evaluates its virtual physics against an internal environment model. But think about what actually happens to physical materials over time.
Right, things break down.
Exactly.
Yeah.
Friction coefficients change as dust gets into joints. The torque of a servo degrades. The structural rigidity of a strut weakens under thermal stress.
Oh, sure.
Even the battery voltage sags, meaning a command for 100% power today provides less physical force than it did a year ago.
So the real robot slowly drifts away from the factory-perfect avatar over time.
Exactly. And what's fascinating here is, if the avatar isn't a faithful representation of the degraded current reality, the solutions the robot invents in the simulation will just be hallucinations.
They'll look great in the mental holodeck, but the moment they are deployed on the physical machine...
They will fail completely. The simulation must continuously calibrate to the dirt and wear of the real world.
Okay, so we have this robot. It realizes that it has a problem. It loads up its incredibly accurate, calibrated mental holodeck to test out solutions. But when it starts daydreaming fixes, it doesn't just randomly invent completely new ways to move its body, right?
No, it can't.
Because if a robot with 15 joints tries every possible combination of movements, the math gets impossibly huge, doesn't it?
The search space explodes exponentially. If you have to calculate the angles, speeds, and timing for 15 different joints simultaneously, you are dealing with millions of potential permutations.
Right.
If the robot tries to search globally across all those combinations to invent a brand new walk from scratch, the processor will simply run out of time. The deterministic deadline will expire.
So how does it survive the math? How does it bound that search?
By enforcing a very strict hierarchical motion representation, this layering is the absolute secret to keeping the recovery computationally tractable.
The paper divides motion into 3 very specific layers. Let's break these down. What is the absolute bottom layer?
The lowest layer consists of what the paper calls primitives.
Primitives.
Yeah, these are atomic, deeply parameterized joint motions. Think of a single isolated command like lift up, push down, or shift right absolute. These are the smallest possible building blocks of movement.
Okay.
And the crucial design choice here is that every single degree of freedom, every individual physical joint has its own dedicated, reprogrammable control subsystem responsible just for these primitives.
So layer 1 is basically just a single muscle twitching.
Right.
But a muscle twitch doesn't get you anywhere on its own. How does it stitch those together?
That leads to layer 2, compound action.
Compound actions.
This is a functional movement assembled from a sequence of those atomic primitives. For example, the action of step forward. A step forward requires a specific timing of lifting up, swinging forward, and pushing down.
Makes sense. And then layer 3 sits on top of that.
Layer 3 is gaits. This is the whole body locomotion, walking, running, crawling. This layer coordinates the compound actions, the steps, across all the different legs to ensure the robot doesn't just fall over while it moves.
So we have primitives, compound actions, and gaits. Twitches, steps, and walking.
Exactly.
But the true genius of this architecture isn't just that it organizes the code this way. It's how it uses this hierarchy when something physically breaks. It relies on what they call a local before global protocol.
This is where the time saving really happens. When a failure is detected, the robot does not immediately go to the gate layer and try to reinvent how to walk.
Right, that would be searching globally.
Yes. Instead, adaptation is attempted first at the absolute lowest affected primitive.
Give me an example of what that looks like in the hardware. How does that play out?
Okay, imagine the primitive command lift up on the front left leg fails because the primary lifting servo has stripped its gears.
Okay, bad news.
Right. The local subsystem for that specific joint realizes it can't execute the command, but instead of panicking the whole system, it isolates the problem. It searches only for a local substitute that reproduces the physical effect of lift up.
Just trying to solve that one tiny problem.
Exactly. It might figure out that if it rotates a secondary lateral servo 90 degrees, flexes the knee and rotates back, it can artificially hoist the leg up just enough to clear the ground.
Wow, so it's micro-adaptation.
Yes.
Think about it this way. If I slam my hand in a door and injure my index finger, I don't sit down at my desk and attempt to relearn how to type the entire English language from scratch.
No, you don't.
I don't reconsider my spinal posture or my desk chair. I just figure out how to awkwardly hit the T key with my middle finger instead. I isolate the damage to the smallest possible unit.
That perfectly captures the essence of bounding the search. You keep the cheap fix cheap.
Keep the cheap fix cheap. I like that.
Only if the system absolutely cannot find a local substitute for lift up does it escalate the failure up the chain.
Right.
If the primitive can't be faked, the system admits defeat at layer 1 and moves to layer 2. It re-synthesizes the entire step forward compound action, perhaps by just dragging the broken leg instead of lifting it.
By strictly enforcing this local before global protocol, the robot guarantees it only spends heavy computational power when it absolutely has to.
Exactly. It prevents the exponential math explosion.
But this raises the most intense technical question of the whole paper. We know the robot adapts inside the avatar. We know it isolates the fix to the lowest possible primitive. But physically, mechanically, how is it rewriting its own software? I mean, it's a machine altering its own base code on the fly. How does it do that?
To accomplish that, the architecture relies on a neuroevolution engine, specifically a system called NEAT.
NEAT, which stands for Neuroevolution of Augmenting Topologies. This sounds like an entirely different branch of computer science.
It is. NEAT was introduced by researchers Kenneth O. Stanley and Risto Mikkelainen at the University of Texas at Austin back in 2001.
Sure.
NEAT is the actual synthesis engine running inside the avatar. During a single high-stakes recovery episode, NEAT can autonomously generate, mutate, and evaluate tens of thousands of candidate control networks in a matter of seconds.
Okay, we need to go deep into the mechanics here. How does a neuroevolution engine actually mutate code? Is it just like randomly flipping ones and zeros?
No. It is highly structured, and it really mimics biological evolution. Standard neural networks usually have a fixed topology, like a set number of neurons and connections, and you just adjust the weights or the strength of those connections.
That's standard machine learning.
But NEAT is different. It evolves both the weights and the actual topology. It can grow new neurons. It can wire entirely new connections between parts of the network that were previously isolated. Every candidate controller is represented as a linear genome, much like DNA.
What does a single gene look like in this robot's DNA?
Each gene is essentially a set of instructions for a single connection. It names an input node, an output node, the mathematical weight of the connection, a bit that turns the connection on or off, and one incredibly special piece of metadata, an innovation number,
An innovation number. Why is that special?
because it solves one of the oldest problems in evolutionary computing. The innovation number is a global historical marking. Every time a brand new structural mutation occurs, say a new connection is drawn between node A and node B, the system stamps that new gene with a unique serial number.
Okay, I follow.
Because two genes that share an origin share an innovation number, NEAT can take two radically different, highly mutated neural networks, line them up side by side, match them gene by gene, and crossbreed them sensibly. This solves the competing conventions problem.
Wait, competing conventions, does that mean the robot's left leg is trying to execute one convention and the right leg is competing with a different one and they are like fighting over movement?
Not quite. It's an internal software problem, not a physical one. Competing conventions happen when you have two neural networks that achieve the exact same successful physical result, but their internal code is structured completely differently. Imagine you and I both write a recipe for a cake. We both get a delicious cake, but you listed the flour first and I listed the sugar first.
Right.
If a computer tries to blindly splice the first half of your recipe with the second half of mine, we might end up with a recipe that has 0 flour and double sugar.
A broken, uncompilable mess.
Exactly. But because NEAT uses innovation numbers, it tracks the historical origin of the ingredients. It knows exactly which piece of code is the flour, no matter where it ended up in the genome. It can splice different networks together without destroying their function.
That is brilliant. But if it's constantly mutating and adding new nodes, doesn't a random new mutation usually make the robot perform worse at first? I mean, a random change to a working system usually breaks it before it gets tuned.
You've hit on the exact reason most evolutionary algorithms fail. A newly added node almost always lowers the fitness of the network initially.
Yeah, that makes sense.
In a pure cutthroat survival of the fittest algorithm, that new experimental network would be immediately killed off because it performs poorly on the first try.
But wouldn't stand a chance.
Exactly. So to protect these young, immature structural changes, NEAT employs a concept called speciation.
Speciation, like separating animals into different species.
Mathematically, yes. NEAT groups similar genomes together based on those innovation numbers we just talked about. If a group of networks shares a lot of the same historical markings, they are clustered into a species. And here's the trick. Networks only compete for survival against other networks within their own species.
Oh, wow. So the weird new mutant ideas are sheltered. They don't have to compete against the highly optimized mature networks right away.
Exactly.
They're given time to mature in their own little niche to see if that weird new mutation eventually leads to a massive breakthrough.
Precisely. Speciation protects topological innovation. But when we get to adapting those layer 2 compound actions, the full steps, the robot doesn't actually want to rely solely on open-ended innovation. It doesn't want to start with a blank piece of DNA.
Because starting from scratch takes too long for the deadline.
Right. For compound actions, the robot leverages factory-tested linked pairs. These are physical actions that are near mirror images of each other. Think of step forward and step back. Or pivot rear clockwise and pivot rear counterclockwise. If the robot breaks its step forward action, it doesn't fire up NEAT and ask it to invent forward momentum from nothing.
It warm starts the process.
Yes. It warm starts by copying the top-performing known good controllers of its linked partner, say, step back. It strips and rebuilds a network that already understands the geometry of the leg, rather than inventing geometry from scratch.
You know, the analogy that jumps out at me here is baking again. If you suddenly need to make a quick muffin, you don't start by inventing the concept of milling grain and applying thermal heat.
Right.
You take a massive, intricate, highly complex recipe for a 3-tier wedding cake that you already know works, and you fiercely edit it down. You cross out the fondant, you cross out the structural supports, until you are left with just a basic batter that fits your muffin tin.
That is an incredibly apt way to look at it, and it describes the most unique software contribution of this white paper, the deconstruction-biased repair heuristic.
The deconstruction-biased repair heuristic. Let's explore that math, because the paper emphasizes how critical this bias is.
Standard NEAT, canonically, starts with minimal structure. It starts with 0 hidden nodes, just inputs connected directly to outputs, and it complexifies over time. It only adds structure when it proves useful.
Start simple, get complex.
Right. But this paper proposes a deliberate, aggressive inversion of that process. Because you are warm starting with your wedding cake, a network evolved for a related but different action. It is packed full of complex structures that the new target action simply doesn't need.
Right, all the fondant.
Exactly. So the system applies a heavy deconstruction bias. It actively tries to delete code. It prunes the network down to the nearest working simplification.
So while standard evolution tries to grow, this system is acting like an aggressive editor, deleting every line of code it can until the program breaks and then stepping back 1 inch.
Yes. And the paper gives specific math for how this pressure is applied over time. The deconstruction favoring mutations are forced to make up a specific fraction defined as 1 over k of all alterations. And the variable k steps up over successive cycles. 3, 4, 5, 6.
Wait, let me do the math. If k is getting bigger, then 1 over k is getting smaller, so 13, 14, 15. That means the pressure to delete code starts incredibly strong, but slowly tapers off as the generations continue.
Exactly. You hit it with a sledgehammer initially to knock off all the obvious excess, and then you switch to a scalpel. And the system knows exactly when to put the scalpel down.
How did it know?
The aggressive deletion stops when either of two mathematical conditions are met. First, if the system measures sudden positive progress toward a viable physical solution. Or second, if the network shrinks to a specific target threshold size.
How does it know what size it's supposed to shrink to?
It's defined as 1 over n of its starting size, where n is calculated dynamically based on the number of starting nodes and links. Whichever of those two conditions is met, first progress or target size acts as release valve. The deconstruction bias is lifted, and standard complexifying neat takes back over to fine-tune the final solution.
I find this fascinating because it really mirrors how humans act in triage situations. In an emergency, you don't have the luxury of open-ended philosophical exploration. You grab the nearest complex thing that kind of works, and you violently hack away everything you don't need until it fits the immediate crisis.
It is absolute triage. And to pull off this level of triage computation, breeding tens of thousands of complex neural networks, running physics simulations, applying deconstruction math, all inside a few seconds, the paper anticipates that standard microchips simply won't survive.
They just aren't fast enough.
Right. It proposes the need for specialized hardware.
What kind of hardware?
A custom layered data flow accelerator, specifically a systolic array.
Okay, we need an ELI5 on systolic array. How does that differ from the CPU running inside my laptop right now?
Okay, your laptop CPU relies on the von Neumann architecture. It has a central processor, and it has memory. To do math, the processor has to reach out to the memory, grab a number, bring it back, do the addition, and then send the result back to memory.
Right.
It's incredibly versatile, but fetching data back and forth creates a massive bottleneck. It wastes time.
Like a chef constantly running to the pantry for every single ingredient, one at a time.
Yes, exactly. A systolic array, on the other hand, is a spatial data flow fabric. It is a massive grid of tiny, dedicated processing elements. You pump data into one side of the grid, and the data flows through the processors like a physical assembly line.
Oh, wow.
Each processor does one specific piece of math and immediately passes the result directly to its neighbor on the next clock cycle. There is no running back to the pantry.
It's a continuous, uninterrupted stream of math.
Exactly. And unlike standard AI chips that are optimized for rigid, dense layers of neurons like you see in ChatGPT, this proposed hardware is uniquely specialized for the sparse, highly irregular, and continually mutating topologies that NEAT produces.
It's built for the messiness of evolution.
Right. It physically advances network nodes per hardware click, updating states across multiple branching paths simultaneously. The silicon physically reconfigures itself to match the DNA of the genome being tested.
That is just mind-boggling to conceptualize. A physical piece of silicon reshaping its data flow millions of times a second inside the crippled leg of a robot on an asteroid.
It is incredible engineering.
But let's ground this back in the physical world for a second. The systolic array runs the math. The neuroevolution engine spits out a winning code in the virtual avatar. The holodeck thinks it has a solution.
Right.
But now, it's time for the moment of truth.
This is the most critical transition in the entire architecture. The new mutated control pattern is burned into the robot's reprogrammable subsystems, and it must physically test the adaptation on its own broken body.
The moment where simulation meets reality. The paper informally calls this the ant dance.
The ant dance. It's a series of cautious, small physical shifts. A slight step forward, a probing shift of weight, a tentative step back.
Just feeling it out.
Yes. The robot is actively testing the reality gap. It is probing to see if the substitute motion that worked perfectly in the frictionless holodeck actually holds against real-world gravity, real abrasive friction, and real uneven footing.
Is there an example of a robot actually doing this dance in the real world? Like, has this been tested?
Yes, there is a very famous precedent. A 2015 paper published in Nature by Antoine Cully and his colleagues. They built a physical hexapod, a six-legged robot,
Yeah.
and they literally snapped one of its legs in half.
Just broke it on purpose.
Yep. And using a system called intelligent trial and error, which leverages Bayesian optimization, the physical robot was able to run a series of very short, stuttering tests on its remaining legs.
The ant dance.
Exactly. And within about 2 minutes of physically twitching and testing, it updated its models, discovered a highly efficient limping gait, and continued walking.
2 minutes. From catastrophic damage to walking again. That's biological speed. But what happens if the ant dance fails? What if the avatar thought it had a perfect, elegant fix, but when the real robot shifts its weight, it completely faceplants?
Well, if the dance fails, a naive system would just keep generating new walks in the same simulation and repeatedly throwing itself at the dirt.
Which would just destroy the robot.
Right. This architecture does something much deeper. If the physical test fails, the system assumes that its initial understanding of its own fault was wrong. It treats the gap between the predicted motion and the observed failure as brand new diagnostic information.
Ah, diagnosis as inference.
Yes. The discrepancy between what was mathematically commanded and what was physically observed is the richest diagnostic signal available to the machine.
Let me make sure I get this. Give me a mechanical example.
Okay, suppose the robot commands the knee joint to rotate 45 degrees. The internal servo sensor reports that the motor did, in fact, spin 45 degrees.
Okay, so the motor works.
Right, but the sensor on the foot pad keeps reading heavy, continuous ground contact the entire time. What does that physical discrepancy tell you?
Well, the motor spun, but the foot never left the floor. It means the leg didn't actually lift.
And if the leg didn't lift, the fault is not in the software logic. The fault is not a burned-out motor. The fault is a snapped mechanical linkage connecting the motor to the leg.
Oh, the motor just spun freely in the void.
Exactly. The robot must use this inference to heavily update its internal self model. It must amputate the linkage in the avatar before it tries evolving another solution. It transitions from simply adapting to its environment to fundamentally learning what its body's physically become.
But wait, this introduces a really dangerous trap, doesn't it?
Yeah.
What if the robot is perfectly fine, but the environment is tricking it?
Tricking it how?
Imagine a robot standing on a pile of loose lunar sand. It tries to walk forward, the sand gives way beneath its feet, and it slips and falls. The physical motion didn't match the commanded motion. Does the robot suddenly hallucinate that its internal linkages are snapped?
Ah, that is the deepest, most treacherous trap in self-modeling. It's the danger of attributing an external environmental disturbance to internal structural damage.
Because if it gets that wrong,
If a robot on yielding sand sees its predictions fail, and it structurally amputates a virtual leg that is perfectly healthy, it ends up permanently crippling itself. It's trying to adapt to a broken body that doesn't actually exist.
it's like a hypochondriac algorithm. It convinces itself it's dying just because it slipped on some ice.
That's a perfect way to describe it.
So how does the architecture prevent that? How does it tell the difference between my physical leg is shattered and I'm just standing on slippery gravel?
The discriminator relies on two concepts.
Yeah.
Persistence and correlation. Before the system rewrites its structural DNA, it interrogates the failure over time and space. An internal fault, a shattered leg, travels with the robot. It is persistent. It recurs consistently across different motions, different speeds, and different orientations.
Right, because the leg is always broken.
But an environmental disturbance, like slipping on ice or sinking in sand, is transient. It correlates with an external signal.
Give me an example of an external correlation.
The robot checks its inertial measurement unit. Is the slip perfectly correlated with a 15-degree downward slope? As the robot shifts its position, does the error change severity depending on which patch of ground it touches?
So it's looking for patterns.
Yes. If the error stays rigidly consistent with the robot regardless of what it's doing, the system confidently labels it an internal fault. If the error fluctuates with the external world, the system classifies it as environmental and protects the avatar from being falsely degraded.
That makes perfect logical sense. It really does. But let's look at the absolute worst case scenario. What if the math is just too hard?
It often is.
Right. What if the reality gap is too complex? The processor is overeating, the battery is dying, and the injured unit is simply running out of deterministic time to run these massive physics simulations on its own.
When an isolated unit exhausts its local computational budget, It invokes the next layer of the architecture. It calls for backup.
It leverages the
Yes.
swarm computation layer. This is where the paper moves from a lone survivor scenario to collective distributed intelligence.
Exactly. When other robotic peers are within communication range, they actively step in to provide two critical life-saving forms of assistance: shared sensing and distributed computation.
Let's look at shared sensing first, because it solves a terrifying problem the paper calls self versus self.
Self versus self, it refers to structural blindness. A robot, much like a human, can only sense itself from the inside, using proprioception.
Okay, what does that mean in physical terms?
Imagine a robot has sustained an impact that physically bent its heavy metal femur by 30 degrees. The internal servos are intact. The internal rotation sensors are reporting that the joint is moving exactly to the commanded angles.
So the robot's internal instruments say it is at factory perfection.
Right. But because the actual metal is bent, the geometry is completely ruined and the leg just drags on the ground.
The robot is fundamentally blind to its own deformity.
Or consider an even more insidious version: a lying sensor. What if a contact pad on the foot has simply short-circuited and constantly reads touching ground?
The system will build a completely delusional avatar.
And waste precious battery life, optimizing a recovery for a physical reality that doesn't exist.
This is exactly what happened to the Apollo 13 oxygen tanks, right? The sensors lied, and the astronauts had to literally look out the window to see the gas venting into space to know the true physical state of the ship.
A perfect historical analogy. An external view is mandatory. And this is where shared sensing comes in. A neighboring, healthy, peer robot simply walks over, looks at the injured unit with its external stereoscopic cameras, and transmits an objective report.
Your left femur is bent 30 degrees, and your foot is 3 inches off the ground.
Exactly. It supplies a geometric truth that an isolated robot can never mathematically obtain on its own.
I love that. It's like you're driving down the highway and your taillight goes out. You literally cannot see it from the driver's seat. Your dashboard doesn't tell you. You need a friend in another car to pull up next to you and say, hey, your light is dead.
And once the injured unit uses that external truth to correct its delusional avatar, the swarm transitions to the second form of help: distributed recovery. They network together to solve the math.
The paper refers to this as forming a Beowulf cluster.
Yes. The concept of a Beowulf cluster dates back to the mid-1990s at NASA. Instead of buying one massive $50 million supercomputer, engineers realized they could lash together dozens of cheap, off-the-shelf personal computers using a local network.
Right.
And they run software that distributes the mathematical workload across all their processors simultaneously, creating a parallel compute fabric.
And the robots do this wirelessly on the asteroid.
Exactly. The injured unit assumes the role of the server. It directs the search because it holds the irreplaceable real-world data, its last known good state, the exact sensor logs of the failure, and the results of its failed ant dances.
So it broadcasts this data packet to the swarm.
Right. And the healthy peers act as compute nodes, spinning up their systolic accelerators to run thousands of neat simulations in parallel.
It's an incredibly asymmetrical relationship. You have one broken robot commanding the processors of 10 healthy ones.
It is deliberately asymmetric. If we connect this to the bigger picture, the damaged unit is the one with the least time, the lowest energy reserves, and compromised hardware.
So the swarm actively spends its collective energy defending its weakest member.
Yes.
Yeah.
The injured unit basically broadcasts, "I am hurt. My time window is closing. Run my recovery search on your hardware and just beam me back the winning code."
But how do the 10 healthy peers divide up the work? Do they just all start guessing randomly and hope someone gets lucky?
No. It's highly structured to avoid redundant work. The server assigns specific search ranges, and the search is escalated logically. First, the peers assume a single additional fault in the avatar. They partition the simulation space.
Okay, so Node A tests if Servo 3 is broken. Node B tests if Servo 4 is broken.
Exactly. If the entire single fault search space is completely exhausted by the cluster with zero viable walking gates produced, only then does the cluster escalate to a double fault search space.
Because searching for 2 simultaneous breaks increases the math exponentially again.
Exactly. And they don't start the double fault search blind. They seed the double fault simulations using the closest near misses from the single fault pass. It is a highly disciplined, distributed Bayesian search.
It's a phenomenally robust architecture. Between the avatar, the neat engine, the systolic arrays, the ant dance, and the Beowulf cluster, it feels like this robot could survive a direct meteor strike.
It's very thorough.
But the white paper points out that there is one specific type of failure that actively tries to trick this entire verification system. It's the absolute worst nightmare of any hardware engineer.
Intermittent faults. The ghost in the machine.
It goes in the machine. Why are intermittent faults so deadly to this specific architecture?
Because an intermittent fault directly attacks the confirmation step. The entire ant dance relies on the assumption of reproducibility. It assumes that if a joint is broken, it stays broken.
Right.
But think about real-world physics. Think of a microscopic wire connection that only opens and loses conductivity when the surrounding metal heats up and expands.
Oh, I see where this is going.
Or a power rail that functions perfectly at rest, but its voltage sags drastically only under the heavy torque of an actual step.
Ah, the robot loads a suspected fix and performs the ant dance. But because the dance is just a slow, cautious shift of weight, the metal isn't hot, the torque is low, so the wire stays connected.
Exactly. The test passes cleanly. The fault is temporarily absent. The avatar clears the error. The system declares itself fully healed, and the robot takes a confident full-speed step forward.
And then the torque spikes, the metal heats up, the wire disconnects, and the leg gives out instantly.
The system was completely tricked.
That is terrifying for an autonomous system.
It is. The author shares a very poignant anecdote from their scientific instrumentation days to illustrate how insidious this is.
Oh, what happened?
A customer returned a 6 degree of freedom pulse DC magnetic tracker, claiming it was faulty. The engineers put it on the test bench, ran all the diagnostics, and it worked flawlessly.
Of course it did.
Right. They stamped it, no fault found, and shipped it back. But the reality was, there was a tiny thermal flaw in a solder joint that only disconnected when the unit reached operating temperature in the field. As the author notes, no fault found really just means fault not present here now.
So how on earth does an autonomous robot deal with a ghost fault that disappears when you test it?
It applies two strategies. First, it carries suspicion forward. A single passing ant dance does not fully exonerate a component.
Okay, so it keeps an eye on it.
Right. If a joint fails and then passes a test, the system keeps that specific channel under a lightweight, continuous watch. If it fails a second time during normal operations, the robot doesn't start diagnosing from zero again. It immediately flags it. Ah, the known intermittent fault has returned.
And what's the second strategy? What does it do once it confirms it's a ghost?
It reclassifies and routes around. If a fault recurs repeatedly, despite passing bench tests, the robot fundamentally stops trying to repair or trust that component. It permanently cuts power to that leg.
Wait, it just shuts the leg off entirely. Isn't that giving up?
It is not giving up. It is the concept of graceful degradation. The paper argues passionately that a leg that works only sometimes is infinitely more dangerous than a leg that never works.
Because an intermittent leg betrays the complex walking math exactly at the moment of highest mechanical stress.
Exactly. A reliably dead leg, however, is a known constant. It is safe because you can plan the physics around dead weight.
Ah, that makes sense.
So the robot reclassifies the unpredictable component as totally dead and falls back to a pre-compiled degraded mode. For example, it triggers a state called appendage 4 non-functional, which results in a 5-legged limp.
But doesn't falling back to a pre-programmed 5-legged limp kind of admit defeat for the whole neuroevolution engine? Why not use NEAT to invent a customized 5-legged walk?
Because doing so would waste precious computational time on a known, highly probable scenario. The paper frames this as the hallmark of mature system design. You do not spend real-time compute budget dynamically searching for the foreseeable.
And losing one leg out of 6 is a highly foreseeable failure mode for Hexapod.
Exactly. The specific motor torques required for a 5-legged limp are pre-compiled, rigorously tested at the factory, and cached on the storage drive before the rocket even launches.
It's an instinct.
Exactly like biological instinct. If a coyote steps on a thorn, it doesn't pause for 5 minutes to invent the mathematical geometry of moving on 3 legs.
Right, the 3-legged trot is a pre-wired instinct. It drops into it instantly.
The engineering principle here is profound. Dynamically compute only the unforeseen and aggressively cache the foreseeable.
Compute the unforeseen, cache the foreseeable. That is a brilliant piece of engineering philosophy. It sounds bulletproof, but to its immense credit, this white paper doesn't read like a marketing brochure. Section 13 is brutally honest about the open problems, the things that still keep these roboticists awake at night.
And they should keep them awake, because no software architecture, no matter how elegant, can permanently wave away hard physical limits.
Let's look at a few of these open problems. First, we already touched on the reality gap. If the internal avatar isn't perfectly calibrated to the degraded physical reality, every single simulation is just a hallucination, and the repairs will fail.
Then there are the strict cost and time budgets. If the custom systolic accelerator chips are too expensive to manufacture, or if the robot is isolated without a swarm to form a Beowulf cluster, the injured unit might simply run out of battery power or slide down a slope before it can compute a viable fix.
It is always a race against the physics clock.
Always.
And speaking of the swarm, the paper brings up a massive issue with shared sensing, the Byzantine fault problem.
Yes, the entire swarm architecture assumes that your neighboring peers are honest and functional. But what if a peer robot has a subtle, undetected fault in its own stereoscopic camera?
Oh no, it will confidently beam over completely corrupted structural data.
And the injured unit will rewrite its own avatar based on that hallucination, and the entire distributed recovery effort collapses. Cross-checking and validating external observers is a major, unsolved cryptographic and structural challenge.
There is also the physical reality of the hardware wearing out. It's easy to say rewrite the code, but physically that means writing to non-volatile flash memory.
Right. Flash memory works by physically trapping electrons in floating-gate transistors. Every time you erase and rewrite that code, which this system might do thousands of times during a complex, neat evolution, you physically degrade the oxide layer in the silicon.
So if you hit the rewrite limit of your flash storage,
Your software adaptability is permanently bounded by physical hardware endurance. The memory chip simply dies.
and lastly, the ant dance itself. Performing a physical self-test with a structurally compromised body in a completely uncontrolled environment. If you shift your weight the wrong way on the edge of a crater, you don't just fail the test.
No, you throw yourself into the abyss. It is a stark, grounding reminder. Energy, latency, thermal expansion, silicon degradation, gravity. Software logic can only mitigate the physical world. It can never fully escape it.
I genuinely appreciate the paper's honesty. It's incredibly rare to read an advanced design architecture that gives you a detailed, bulleted list of all the ways the system might still catastrophically die. It makes the engineering feel grounded and real.
It reflects the maturity of a discipline that has learned hard lessons from real-world deployments.
It really does. We have covered an immense amount of ground in this deep dive. From watching a cane toad strike a mealworm, we explored the elegance of morphological computation, letting the physical body do the thinking.
We stepped inside the mental holodeck of the virtual avatar, where the machine daydreams its own physical trauma.
We unpacked the neat neuroevolution engine, tracing innovation numbers to solve competing conventions, protecting young networks through speciation.
And applying that aggressive deconstruction bias to hack down a complex network into a triage solution.
Editing the wedding cake down to the muffin. We visualized the spatial data flow of the systolic hardware. We watched the robot perform the physical ant dance to probe the reality gap.
We saw how an injured unit can recruit a swarm to form a Beowulf cluster, lending their eyes and processors to solve structural blindness.
And we confronted the ghostly nightmare of intermittent faults by graciously accepting the five-legged limp.
The overarching lesson of this architecture is a fundamental shift in how we build complex systems. We are moving away from brittle, centralized, top-down engineered perfection.
And moving toward messy, bottom-up biological resilience. Resilience that lives at the edges of the system, capable of accepting damage and continuously routing around it.
Exactly.
And that shift changes how you view everything. For you listening, think about how this philosophy applies to the systems in your own life. We spend so much energy trying to build perfect plans, perfect supply chains, perfect corporate schedules. We try to be Swiss watches. But the real world is messy.
It is.
If a piece of metal on an asteroid can look at its own damaged state, except that it can never return to perfectly normal, and instantly prune its own code to find the most graceful way to keep moving forward, what could we achieve if we applied that same deconstruction-biased repair to our human systems, our cities, our logistics networks, or even our own personal setbacks? When your perfect plan inevitably shatters, maybe the goal isn't to pretend you can fix the broken pieces. Just like the animal in the wild, maybe the goal is to survive the messy reality, isolate the damage, and learn how to do the ant dance. Thank you so much for joining us on this deep dive into the resilient edges of engineering. Keep questioning the perfect plans, keep adapting to the reality gap, and we will see you next time.